Hey, today we're going to look at an important result known as the mean value theorem. And here's what it says. It says, suppose we have a function f that's continuous on the closed interval from a to b, differentiable on the open interval from a to b. Then that means that there's some point c in the open interval from a to b, such that the derivative at c is equal to f of b minus f of a all over b minus a, which is the slope of a secant line from a to b. And this is sometimes rewritten by multiplying through both sides by the denominator b minus a, as f of b minus f of a equals f prime of c times b minus a. This is a very important theorem. In a moment, we'll take a look at a proof of it. The proof of it will use Rolle's theorem, as I promised in the last video. But first, let's look at a picture. Here we have a graph of the function y equals x squared. And if we look at it on the interval from -1 to 4, then it's certainly continuous on that closed interval and differentiable on that open interval, because it's continuous and differentiable everywhere. And what the mean value theorem is saying that somewhere between -1 and 4, there's a point where the slope of a tangent line is equal to the slope of this secant line from -1 to 4. And it's not hard to see that this is the case. Here we have a point where the slope of the tangent line is clearly the same as the slope of the secant line. You could do a little work and find out that the x value at that point is 1.5 or 3/2. And so the derivative at that point is precisely f of 4 minus f of -1 all over 4 minus -1. And that's what the mean value theorem says must happen. Anytime you have a function that's continuous on a closed interval and differentiable on the open interval, there is some point where the derivative is equal to the slope of the tangent of the secant line between those 2 points. Okay, so let's work on the proof. And the proof is really rather quite slick. It starts, we define this new function h of x that at first looks quite complicated. It's f of x minus f of a minus this crazy number times x minus a, but that crazy number is just the slope of a secant line, so it's not surprising that it shows up, the slope of a secant line from a to b. And in particular, you should remember that that whole thing in the parentheses there, that f of b minus f of a all over b minus a, is just some number. The a and the b are fixed. X is the only variable here. So we're defining this bizarre-looking function h. You take a minute and see if you can compute what h of a is equal to. So pause the video, think about h of a, and see if you can come up with what it's equal to. And hopefully that wasn't too hard. If you didn't get it, it's not hard to see that h of a is equal to 0, so go back and look again, and you'll see that h of a is actually equal to 0. All right, the next one's slightly trickier. See if you can figure out what h of b is equal to. Once again, pause the video, have some fun for yourself, and figure out what h of b is equal to. And with any luck, you came up with the answer that h of b is also equal to 0. Because it is, this function is very carefully defined so that h of a is 0 and h of b is 0. The function h is constructed from a bunch of continuous functions and numbers that are multiplied by obvious continuous functions, and so is itself a continuous function on AB. And I claim that it's also differentiable on the open interval from a to b. If you'd like to join in the fun, then take a moment. The way I'm going to show that it's differentiable is by taking its derivative. You could do that. Take a moment and see if you can figure out what the derivative of h is. And so pause the video if you like. If not, I'll be doing it in just a moment. You take the derivative of h and you find, well, the derivative of f is f prime, the derivative of f. The derivative of f of a is 0. And then we've got this number that is the slope of a secant line times this x minus a. Well, if you distribute there, the derivative of the number times x is just the number. And then the number times a is just some other number, so its derivative is 0. And so you come up with, yes, h is differentiable. Here's its derivative. Okay, we went through a lot of trouble to come up with a function that was continuous on a closed interval, differentiable on the open interval, and had the same value at the two endpoints. The purpose of doing that was so that we could apply Rolle's theorem. And Rolle's theorem tells us that there has to be some point C in the interval from a to b, such that the derivative at c is equal to 0. And since h prime of c is equal to 0, that tells us that f prime of c minus this quantity f of b minus f of a all over b minus a is equal to 0. And that gives us what we were looking for, that at this point c, the derivative of the original function f is f of b minus f of a all over b minus a. And that completes the proof of the mean value theorem. The mean value theorem is very important and useful in its own right, and yet it has a number of corollaries, where a corollary is a theorem that follows very easily, or at least relatively easily, from some other theorem. And the mean value theorem has a number of interesting and important corollaries, so we're going to look at those, a few of those right now. And the first of these is this one, that if the derivative of some function is 0, for all the x values in some open interval, then the function is necessarily constant on that interval. It has the same value everywhere in that interval. And here's the proof. We start by choosing two x values in the interval from a to b. I'll call them x1 and x2, and I'll pick them so that x1 is the smaller one. Then f is continuous on the closed interval from x1 to x2 and differentiable on the open interval. The differentiable on the open interval part is completely obvious because x1 and x2 are contained in the interval from a to b, and it's differentiable on that entire open interval. The continuous on the closed interval from x1 to x2 part is slightly subtle, but we know that the function is differentiable at x1 and at x2, because these are points in the interval from a to b. And we know that any place where a function is differentiable, it has to be continuous, because we already showed at some point in the past that if a function is not continuous, then it's not differentiable. And so what we've done is we've set up the hypotheses of the mean value theorem for this function f on this interval from x1 to x2 contained inside the interval from a to b. And so the mean value theorem tells us that there is some point c where f of x2 minus f of x1 is the derivative at c times x2 minus x1. That's in that second form, the equivalent form of the statement of the result of the mean value theorem. And how does that help? Well, it helps because we know the derivative at c. C is some point between a and b, and our hypothesis to the corollary is that the derivative is 0 everywhere between a and b. So f prime of c is 0. And that, of course, makes f prime of c times x2 minus x1 equal to 0. And that tells us that f of x2 has to equal f of x1. And so, in other words, we picked two arbitrary points between a and b and found that the function has to have the same value at both of them. And so that means it has the same value at any 2 points between a and b. It's a constant function on the entire interval. Here's the second corollary. Suppose you have two functions, f and g, whose derivatives are equal on some open interval from a to b. Well, then the functions have to differ by a constant. The first function is the second function plus some constant for all x in the interval from a to b. And here's the proof. It's another one where we start by defining some new function h. H of x in this case is just f of x minus g of x. And then if we take the derivative of this function h, we get that the derivative of h is f prime of x minus g prime of x. And since f prime of x is equal to g prime of x, we get that the derivative is 0 everywhere on the interval from a to b. And by the previous corollary, the one that we just proved, that means that h is a constant function. Its derivative is 0, so it has to be a constant. And if we give that constant a name, k, for example, and let h of x equal k, well, h of x is f of x minus g of x, so we get that f of x minus g of x is equal to k. And just as we claimed, f of x is g of x plus the constant k. So that completes the proof of this second corollary. Finally, this third corollary will be very important to us. It tells us that if the derivative is positive on some interval, then the function is increasing on that interval. On the other hand, if the derivative is negative on some interval, then the function is decreasing on that interval. Okay, let's start the proof. It goes very similarly at the beginning to our proof of the first corollary. We pick two x values, x1 and x2, in the interval that we're talking about with x1 less than x2, and we argue that the function is continuous on the closed interval from x1 to x2 and differentiable on the open interval from x1 to x2, which is certainly true because we know that the function has a derivative on the entire interval I. It's either positive or negative, depending on which half of the corollary we're proving. And having set up the hypotheses of the mean value theorem, we now get to use the mean value theorem. It tells us that there exists some point C between x1 and x2, such that f of x2 minus f of x1 is equal to the derivative at C times x2 minus x1. Okay, let's see if we can prove the first statement of this corollary. So we'll assume that the derivative is positive on the entire interval. Well, if that's the case, then f prime of C is positive. And since x2 is greater than x1, x2 minus x1 is positive. And so the entire right-hand side of the equal sign here is positive. And if that's positive, then so is the left-hand side of the equal sign. And that means that f of 2 minus f of x1 is a positive number, or f of x2 is bigger than f of x1. Well, x1 was to the left of x2. If f of x2 is bigger than f of x1, that's what it means for a function to be increasing. As you go from the left to the right, the function values are getting bigger. And then to complete the proof, suppose instead that the derivative is negative on the interval. Well, then f prime of C is negative. x2 minus x1 is still positive because x2 is the bigger number. And so a negative times a positive is a negative. And so we get that the right-hand side of the equation is negative. And that makes the left-hand side of the equation negative as well. F of x2 minus f of x1 is negative. And so f of x2 is less than f of x1. And that's what it means for the function to be decreasing. As you go from the left to the right along the x-axis, the function values are getting smaller. So that finishes the proof of this corollary. Okay, that was the mean value theorem and a few of its important corollaries. We'll use them all at some point or another. The third one will become very important very soon when we look at something called the first derivative test. But for now, there's no homework directly on the mean value theorem. See you soon.